I'm Nevin Lieber. I work on C++ standardization, SYCL standardization, and Kokkos. And this is going to present about like 2/3 of the fundamentals, the short course we have on our website, on the Kokkos website. I'll do a little bit of like running the exercises because I mean this is very compressed, limited time. We have a whole lecture series if you want to get much more in detail of Kokkos. I mean, basically start out at github.com/Kokkos and you can find everything from there. So it's like, why do we need Kokkos? What's the ecosystem look like? And what's the team? So this is, I mean, these are slides from 2020, but you know, it's we want to run on, you know, all the platforms that are coming out. That's the goal. And the reason you want to use a framework like Kokkos or Raja is because if you're writing non-portable code, then you have to rewrite parts of your application every time the hardware changes, and that gets expensive, you know, both in terms of, you know, labor costs as well as just in time. So this is, you know, a programming model for performance portability, and it's a template library on top of CUDA, HIP, OpenMP, SYCL, pthreads. And the aim is to be descriptive, not prescriptive. We don't want to tell people how, you know, how to write code. We just want to, like, you know, here's what the interface looks like, you know, call it. And we also want to align with C++ standard. As things get added to the standard, we want to adopt them, and vice versa. Things we work on, if we think they're applicable across a wide variety of architectures or domains, we propose putting them into the standard. Things like atomic ref came from the Kokkos group initially. And it's an open source project, and we have hundreds of users around. So here's what the ecosystem looks like. I mean, you know, if you look at the core, there's, you know, parallel execution and parallel data structures. Then around that we have, you know, like linear algebra kernels and graph kernels. We also have like debugging and profiling and tooling built in, and lots of documentation. There's tutorials, we'll do boot camps, and we'll do support, a lot of which we do over Slack. You know, again, we're across a bunch of national labs. And yeah, we want to support the C++ standard. For instance, in C++ 23, one of the flagship features is looking to be MD-span, which initially came out of Kokkos views, and I'll get into what a Kokkos view is in a bit. As I said, the place to start looking is github.com/Kokkos. You can find the lecture series there. You can find these slides there. I'll also put these slides up on the performance workshop site, GitHub. Wiki, and it has an API reference, and we are currently revamping that to make it much better. And we're putting a fair bit of time into it. And the best way to get a hold of members of the team is over Slack. So here's just like the, you know, basics of how Kokkos works. So if you have a, you know, normal sequential loop right here, we want to map that to be able to execute on various devices. So each iteration of computational body is that's what a unit of work is. The index, you know, says, you know, I'm working on this one particular piece, and the range says how much work total I need to get done. And what you do is you just give an iteration range and a body, a kernel of Kokkos, and then Kokkos will decide how to map that to the hardware. And like Raja, like we use, you know, functors or function objects, most common of which are lambdas. Oh, they, you know, for both, they need not actually be lambdas. You know, you can have hard-coded ones. And all lambda really does is it writes this in a much more convenient way. It's a struct, it has some data, it will have some, you know, it could have some data with it, and it has a function call operator. And the way you execute it is you call Kokkos parallel 4. You The simplest one is you just pass the number of iterations and the functor to do the work. And so that functor would have something that takes an index as a parameter and do the work for that index, that one piece of work. The ordering and concurrency is, of course, not guaranteed by Kokkos because we're just, we're just mapping to hardware. So here's an example where you have atomic force functor. It has atomic forces, which is an array. It has a data type, some data in it. And it's got a function call operator that takes an index and updates that element in the array. And the way you would execute that inside Kokkos is you would call parallel for, pass the number of atoms you want to process, and pass in a functor. But this stuff can't, Kokkos has been around a while, and before C++ 11 we didn't have lambdas, but lambdas are much more concise. Again, lambdas are not magic; they just generate functors. Now you need to capture by value because, among other things, it has to be able to get the data to the GPU or whatever device the code is being executed on. Generally, you don't want to capture things like vector because it will copy the whole contents, and also the memory is probably not in the right space, not in the right place for executing on a device. So how does this look compared to Openmp? I mean, it's conceptually the same thing, right? In Openmp, you have a pragma OMP parallel for, and that says, parallelize this for loop from 0 to n. And so in Kokkos, you just call Kokkos parallel for, you pass n, and then you pass a functor that does the work. So it's, trying to be as close as, we don't want to have brand new ways of doing it. We want to be as close as possible to what people are used to in other paradigms. So you want to do a Reynolds numerical integration, right? So this is kind of what it looks like in sequential code. So how do we parallelize this, and how do we do it correctly? So again, we have this is the range, right? This is how much, what we want to compute over, right? Each piece of work. However, if you're passing a lambda, again, if you notice, you're passing by values. So the total integral variable inside the lambda is a different one than the one that's outside the lambda. And it's also const. You can't modify it. And you really want to modify the one outside the lambda. So one idea people have had is, okay, pass a pointer to it, right? Because you can pass a pointer by value, and then you should be able to refer to it. This, even if the memory is accessible, this introduces a race condition because the lambda is run across multiple GPUs. So there's a race condition here. So this is generally not the way you want to write things. And the more fundamental problem with this is it's the wrong pattern, right? This is not what you want parallel for, right? You want to use reduction, right? Which we all know is right. It's just it's how you combine work into a value. So with Openmp, right, you would say it's a parallel for reduction over plus. You want to put it into final reduced value. And in Kokkos, right, it's again, conceptually the same kind of thing, right? You say how much, there's n things I want to do it over. Here's the functor, and like final reduced value in here it'd be passed in by reference. So that way that'll ultimately be what's updated when the reduction is done. So the functor takes 2 parameters when it's called. The first is the index of what piece of work you're working on. And the second is by reference, the value to update. That's a thread private value. And right, those will eventually be added into total integral. But it's it itself is not the final reduced value. One thing that helps in debugging and what you can do in Kokkos is you can name your kernels. And really, there's no reason not to. Right? It takes a standard string argument and internally just copies the data into an internal data structure. I think it's 128 bytes, but I'd have to look to be sure. And especially if you're profiling or debugging, it's very handy to have to name things. So one of the first exercise is doing the inner product. And so in order to do Kokkos, right, it's thing that, right, you include Kokkos core at HPP. That includes everything having to do with Kokkos. You then call initialize, which will set up Kokkos, and at the end of your computation, call finalize. And there is a Kokkos scope guard in camel case, which will also do that if you want a more C++ish way. Personally, don't like the name scope guard. It doesn't really tell you what it's guarding, but. And then the exercises have some command line arguments. I'll show in a bit. I'll show how to run these if you wish to. Again, this is a kind of condensed talk. And we've also kind of changed the way we compile using CMake now, even for the exercises. So there are 3 data parallelisms. There's parallel for, there's parallel reduce, and parallel scan. And so there's like, the pattern, which is the operation you want to do, the policy, like how do you go about dividing up the work? And the body is, actually computing the work. And the body, again, provided as function objects or lambdas. And they handle a single work item. Now, the next important part is a view. And the view abstraction is pretty simple, right? So you have you have an array of data, right? Double star x equals new double star y equals new double, and right, you want to perform this. So the problem here is that because we call new, that memory is allocated on the host, not on the device. It may not be accessible from the device, depending on what the backend is. So we want a way to store, multi-dimensional arrays that we can, talk to the GPU, and that's what a view is. It's a lightweight class. It's a pointer to data and a little metadata. It's got a name, and a reference count, and it's templated on the data type. And there's a couple other things, and I'll get into a few of the other parameters. We try to pick the correct defaults for things, but sometimes you're doing things that are more complicated, so you have to specify more template parameters in order for that to happen. So here's kind of a high-level view. Instead of allocating the array, we have view. Now, what this double star means, it doesn't mean pointer to double. What it means, it's a double, and star means that its dimension, its size is determined at runtime, not at compile time. Again, you pass it in by value, and now we use the parentheses instead of square brackets. Right? Square brackets until C++23, we can't use those for more than one dimension. There are language changes being made to C++23 as to help with them. They help with MD-span so that we can actually start using square brackets, and Kokkos will likely adopt that as it hits compilers. And views, again, they're just like share pointers, right? They're basically reference counted. So you copy them into your functors. And you can have 0 more dimensions, right? So the number of dimensions is fixed at compile time, but the size of each dimension can be either specified at compile time or at runtime. And these examples, like the view double star star star, that's 3-dimensional, and all 3 sizes are specified at runtime, via N0, N1, and N2. Right, view double star star, square bracket N2, that's also 3-dimensional. The first 2 dimensions are provided at runtime. The third one is provided at compile time. And the way this is, runtime size dimensions must come first. MD-span and the C++ standard instead of using this concise notation, uses standard std : dynamic _ extent to say which things are dynamic and just numbers for which things are static. So you can mix and match as you please. And this is all done really, for efficiency. Allocations and views, I mean, you have to ask for an allocation. They don't happen implicitly. You don't want to hide the runtime cost. Copy, construction, assignment, they're shallow. It's just copying a pointer and updating reference count. They really are just like shared pointers. So here in this view, right, three-dimensional view, C is a reference, just produces a reference to B. So even though, right, B 0,2 modifies, assigns 2 to it, C 0,2 assigns 3 to the same spot, so 3 gets printed. And you can query a view to get all the aspects of it. You can get its label, whatever you need. If you're writing more generic kind of code, this stuff is very useful. And exercise, which I'll be skipping. Next, we have what's an execution space, and that's really the abstraction for where to run code, right? And there's serial, threads, Openmp, CUDA, HIP, SYCL. As things come out, the plan is, we want to port to them. We want this to work across as much as possible. So if you need to change the space, right, again, you can give it a range policy, right? It's kind of more general for parallel fork than just saying the number of things. You can say where it is, the execution space. Execution spaces themselves must be, initialized and finalized. And one thing is functions must be marked with a macro for non-CPU spaces, and lambdas must be marked with a macro for non-CPU spaces, because certain architectures, such as CUDA, required decorations. Which is like CUDA requires _ device, _ host to say that this inline function is available both on the device and the host. So we use the macro to portably say, based on your backend, it should just work. And there's a Kokkos Lambda macro, which does the same thing for capturing by value. Now, go along analogous to execution space, there's a memory space, and that's, where is the data? Now, and so the view has to know where the memory space is at compile time. And it's, again, if it's not the default one, then you have to specify where it is as a template parameter. Again, right, there's host, CUDA, SYCL, etc. Right, if you have something in an execution space, it has a default memory space, which is what you would expect. And if no space is provided, it would default to the default memory space or the default execution space. So these two are equivalent calls. I mean, C++ power lines, they're slightly different types, but they, effectively do the same thing. And so if you have a host view, right, in host space, right, you can just say, okay, this is a two-dimensional array of runtime, of runtime sizes. And if you want it in CUDA space, again, all you got to do is change the template parameter, and everything should just work. So here, because this is in CUDA space, right, this array reference will not work because you can't read from the file. And similarly, because this array is in host space, it can't be read. It can't be read inside CUDA. And the solution is, I mean, you can either, say where the memory should be, or you can also use what we call mirroring. And mirrors are views of the equivalent arrays, possibly in different memory spaces. So you would just, if you have a view in some other space, you would just say, create mirror view, and that will mirror the data, copy the data if necessary to, in this case, host. So you can, create a host view, which is, you can have a view on a device, right? Host view, populate the host view, and then use what's called the deep copy function to copy it back into view. Like, this is C style parameter, so it's destination, comma, source. And then you can just launch a kernel because the view is, again, is in device space. And if you need to look at it again, you can use deep copy to copy the view back into the host view. If you need to, like, maybe you wanted to print it out. So now if the view is host space 2, then a copy is not made, right? It's really trying to be, performance portable and efficient. So if the host process cannot access the view's data, then it gets copied. Otherwise, it will reference the same data. And create mirror always allocates data. Yeah, but again, this is being very explicit, right? We're not trying to hide allocations. We're not trying to abstract those away because that can matter for performance. And so data stored in views are pointers to multi-dimension arrays. And these views abstract away, platform-dependent allocations, deallocation, and access. Heterogeneous nodes can have one or more memory spaces, and mirroring is for getting fast access in host and device memory. And you control where the parallel code is run by a template parameter. Now, another thing views can handle is layout. So for instance, if you have this kind of code, like, what is the best way to access the data, in layout data in A? Right. So there's, there's two, you can have more, you can also have strides, but like layout left is like Fortran layout, right? Column major, right? Layout right is like the usual default C, C++, and Java layout for memory. And again, this is another template parameter that you pass into view if you need to change the default, or you want to specify exactly what it is, right? But the two most common are layout left and layout right. Again, layout left, leftmost index is stride 1, right? The rightmost index is stride 1. If not specified, then for like CUDA space, layout left is the default. For host space, layout right. You can write your own, and it's like 50 lines of code. And also, this is also for MD span there's also a layout template parameter that is also passing into the upcoming MD span in C++ 23. So thread independence, right? So like once a thread reads D, does it need to wait? Well, the CPU, they're independent. GPU, they tend to be synchronized. So for host space, you want to cache them, and like in CUDA space and other GPUs, you want to coalesce them. And this can have significant performance impact. So the rule of thumb is Kokkos index mapping and default layouts provide efficient access if iteration indices correspond to the first index of the array. And I mean, that's really why those things that row major and column major are picked. It's all about efficiency. And again, to summarize, right, every view has, can take a layout as a compile time template parameter, right? Layout right and layout left are the most common. The default for hosts is layout right, and the GPUs is layout left. It's an extensible mechanism. Performance, you want caching on a CPU and coalescing on a GPU. And that's about all I'm going to cover in this. I can try to like show you like a short demo, like how to get Kokkos running. Let me try sharing my terminal screens. That's all I want. Sorry. No, that will work. Wait, 1 sec. Ah, got it. Okay, on the left side, I'm on theta, and on the right side, I'm on one of the nodes. Sorry, left side, I'm on the login node. The right side, I'm on one of the other nodes. And if you want to get started with Kokkos, it's, we have directions up on the Conperf Workshop GitHub. So what you would do is you would make a directory for Kokkos. Doesn't really matter what it's called. Then you want to clone the repository. And then you want to build it somewhere. On Theta, you want to do modulo Intel, PCC, and CMake. So I'm not an expert at the cray stuff. You want dynamic linking. And all you need is CMake to build it. And we explain what these options are. Right, they'll get released here. The compiler on this on the cray is capital C, capital CC. The architecture building for is KNL. Install prefix is just where Kokkos is going to be installed, and that's a current directory / install. I want to enable Openmp and serial, and I don't want to build tests. And it's actually fairly fast. If you're not building tests, it's fairly fast to build once CMake is done. And you can just do make J install. There's a bunch of deprecated warnings. The things that shouldn't matter. In general, it's hard to get rid of warnings in general frameworks of things because different compilers generate different sets of warnings. And in order for other versions of other CMake commands to get it, we want to export the install path, the CMake prefix path. Now let's go out of the build directory. And if you want to get the tutorials, clone that. So let's go, and we'll go into one of them and we'll build it. CD Kokkos tutorials. So here you'll see, I mean, this is, so the way it's organized is that each of the examples has where you begin and then solution to it. It's kind of a primitive make file if you really need to use make. It's The much better way is to use CMake. So what I would do is I would create a build directory. And just use, as long as you're still in the same environment that you build Kokkos with, CMake ... will just do the right thing. And make. And then go over to the node. Right, there's the executable, and just oh, sorry, my fault, since it's not the path. That normally works. I don't think I have to shred you on a node again. Maybe I was on the node too long. Try one more time. Sorry. I was logged in hoping to avoid this. Yeah. Sorry. Yes. All of them, just in case.
Nevin, the font is just barely at the edge of readability. I don't know if you might be able to
Does
increase.
that help? Does that help? Does it get better? Did it get bigger?
Yes. Oh, that's better. Yeah. Oh, that's good.
Oh, I forgot to. Yeah, so that's basically how you run Kokkos. That's pretty much the end of my presentation. Other questions?